In this mini case study, I will show you how to implement a dose-dependent bioavailability. For all administrations, several situations can lead to an apparent dose-dependent bioavailability, either increasing or decreasing with the dose. First, we can have a saturable first-pass effect. A first-pass effect means that the significative fraction of the dose is lost before reaching the systemic circulation. For instance, it can be that the dose is metabolized by gut wall enzymes while being absorbed, or the drug can be metabolized by hepatic enzymes as the blood from the gut flows through the liver before reaching the rest of the body. If this pre-systemic metabolism saturates, then for high doses, a larger fraction will reach the systemic circulation compared to small doses. This means a higher absolute bioavailability for higher doses. On the opposite, the bioavailability can also decrease with the dose. It can be the case when the absorption of the gut walls is via carrier-mediated transport, which can saturate at high doses, for instance. Let's see how we can take this into account by developing a model for a concrete dataset. In this dataset, the drug concentration has been measured after a single dose and different dose levels have been tested. I have already loaded the dataset in Monolix, and we can see that in addition to the usual ID, time, observation, and amount columns, I also have a dose group column that records the dose for each individual, and it has been tagged as a categorical covariate. This is important to more easily see dose-related effects. If I open the data viewer, I can have a look at the data. Maybe let's check on log scale, and I'm gonna also color by dose so that we can see a bit better what is going on. And here we see that we have quite a lot of data during the absorption phase, and the elimination phase looks linear, and I have 5 different dose levels. To model this dataset, I have chosen a one compartment model from the PK library, parameterized with the absorption rate Ka, volume V, and elimination rate K. I have set the initial values, and this model has already run, so we can directly go to the results, where we see the estimated population parameters and the reasonably small standard errors. In the plots, the individual fits look pretty nice for all individuals, so both the small and high doses. In the observation versus individual prediction on log-log scale, it looks pretty good too. However, if I check the visual predictive check, I can see some misspecification here for the 10th percentile. If I want to look in more detail, I can stratify by dose group. And here we see that for the small doses, the prediction from the model is above the data, but it's the opposite for the high doses. So there is something wrong in the model, and it seems to be dose related. To investigate the dose effect in more detail, I can look at the parameters versus covariate plot to check if the individual parameters tend to vary with the dose. And I can see that it's a case for the volume here. This visual observation is also supported by the statistical tests. Here I can see that the random effects for the volume differ significantly for the different dose groups. Of course, it is not the volume itself that changes with the dose, but the bioavailability. Remember that if I have only oral data, I'm in fact estimating V divided by F and not V directly. This is the analytical solution for one compartment model. The amount that reaches the systemic circulation is the administrated dose multiplied by the bioavailability. If I have only oral data, I cannot estimate V and F separately, but only V divided by F. So what I see in the plot is that V divided by F is decreasing as the dose increases. If we assume that the volume of distribution is constant, then it means that the bioavailability is increasing with the dose. We can come up with different formulas about how the bioavailability changes with the dose, but usually a simple Emacs model is sufficient. So we can write this formula here with Fmax, the maximal bioavailability, and D50, the dose at which the bioavailability is half the maximum. If we put this back into the equation, we obtain the following, but here the problem is again the same. V and Fmax appear only here as a factor, so I can not estimate them separately. So I can rewrite this into this formula here, where the apparent volume is in fact V divided by Fmax. And just for convenience, I can call this term Fr. To write this in MLXtrans language, I can use a pk model macro and add an additional parameter Fr. The keyword that is recognized by the pk model is called P for proportion of the dose absorbed, so I write P equals Fr. Now I need to define Fr, and as you can see, I need the dose information for that. There are two ways to get this information in the structural model, either via a dose-related keyword, so I can use this AMT dose keyword in the model. It holds the value of the amount of the last dose, and then I just write it like this. And the second option is to use a regressor that contains the dose information. So I would first have to implement the regressor in the dataset, declare it as a regressor, and then use it in the formula. So let's check the first method first. So starting from my previous model, I'm gonna use the last estimate to start from good initial values next time. Go to the structural model tab and open the model in the editor and modify it in order to introduce the dose-dependent bioavailability. So I'm going to write P equals Fr, and I'm defining Fr using the AMT dose keyword. As you can see, it highlights in green, so it means that it is properly recognized as a keyword. And I should not forget to add D50 as a new parameter here. I can now save this under a new name. D50, save, close, and load this new model file. For the initial value for D50, I should take something that is in the range of the doses I have used in the dataset. So let's start with 15, for instance, set as initial values. And for D50, I will also remove the random effects. This is because in this dataset, I have only one dose level per individual, so I will for sure not be able to distinguish between the random effects of the volume and of the D50. So I'm removing them on D50. I can now save the project. Let's call it D50 and run. In the plots, the VPC is nice now. Also, if I stratify by dose group, and if I check the likelihood, it has improved by 40 points. So that's one way of implementing a dose-dependent bioavailability. However, if you have several types of doses, such as IV and oral, then the AMT dose keyword does not permit to distinguish between the different types of dose. So in that case, the best is to encode the dose as a regressor. Let me show you such a project. So I'm gonna open this one here. So it's the same dataset, except that I have duplicated the dose column and tagged the second one as a regressor. In the structural model, I have this dose reg as an input and declared as a regressor, and then instead of using the AMT dose, I use the regressor information from the dataset directly. All the rest is the same, and the VPC also. So that's the second way of doing it. To finish, the take-home messages are the following. It's good to have a column recording the dose groups tagged as a categorical covariate for stratification. Most of the time, simple formulas for the bioavailability are sufficient. And quite often too, the inter-individual variability on the D50 parameter cannot be estimated, so the easiest is to just remove it. Have a nice week!